So I would like first would like to invite Dr. Dhruva Chakraborty, Honorable Principal of BN College Dhubri, to inaugurate this webinar and
So,
address the gathering. Over to you, sir.
so thank you, Malavika. Namaste. Good morning to everybody. Uh, I would like to welcome all of you to this particular webinar on behalf of BN College. Little brief introduction about BN College because there are many participants who are not familiar with the college. This college was established in 1946 in the town Dhubri, which is the district headquarters of Dhubri district and situated on the bank of river Brahmaputra. The college, at that time, the college was the only center of higher learning in the western part of Assam. The Dhubri district, to get introduce you to the geographical location, the Dhubri district is in the western part of Assam, bordering West Bengal and Bangladesh. It has an international border with Bangladesh. So at that time, the college was the only center of higher education, higher learning in the western part of Assam. And many students from different part of Assam as well as from West Bengal studied in this college. And we are proud, they are proud alumni of this college. Right now, the college offers undergraduate course in Science, Arts and Commerce, as well as post-graduation in chemistry and SMEs. Since it is a webinar of chemistry department, so I would like to mention that the chemistry department, the PG department of chemistry, the laboratory of the PG department of chemistry rather, is recognized as a center for PhD studies as well by Guwahati University. And there are two research guides who are conducting research through their students in the Department of Chemistry in BN College, leading to PhD for the students. So I would like to welcome all of you to this webinar on behalf of the Postgraduate Department of Chemistry as well as BN College Dhubri. We are extremely thankful that Dr. Suresh Bora, synthetic organic chemist from Toronto Research Chemicals, has agreed to participate as a resource person in this particular webinar, in spite of it being a very odd hour for him because it is at midnight at Toronto. So we would like to thank you, sir, for accepting our invitation. We are extremely lucky that Dr. Brijesh Pare, Professor and HOD, Postgraduate Department of Chemistry, Madhav Science Postgraduate College, Ujjain, who is also the President of Association of Chemistry Teachers, is with us and acting as resource person in this webinar. I sincerely hope that the webinar on insight into research in chemistry will be extremely enlightening to all of us. I am also looking forward to learn something because I am also a student of chemistry. And with that note, I declare that this webinar is open. So thank you all. And I now hand it over to Malavika.
Thank you, sir, for your enlightening speech. Now, I'm going to introduce the first speaker of our session, Dr. Suresh Bora, who is presently working as a synthetic organic chemist in Toronto Research Chemicals, LGC, Toronto, Canada. So, after MSc in 2005 from Andhra University, Visakhapatnam, Dr. Bora worked as senior chemist at Milan Laboratories Limited, Hyderabad, followed by as senior research associate at Jubilant Chemsys Limited. After that, he done his PhD in 2016 from IICT Hyderabad. So after doing PhD, he joined as a postdoctoral fellow from 2016 to March 2020 at McMaster University, Hamilton, Canada. His research interest includes synthesis of biologically active natural products. He has a number of publications in various journals like Tetrahedron Letters, European Journal of Organic Chemistry, etc. So today he is going to deliver a speech on isolation, synthesis, and semi-synthesis of some important bioactive molecules. So looking forward for your presentation. Bora sir, over to you.
Good morning to you all. Firstly, I thank BN College, Dr. Dhruva Chakravarti, my friend Partha, Ashwini, Coordinator Malvika, Department of Chemistry, BN College, for this opportunity to speak. I am Suresh. I did my PhD in Organic Chemistry at Indian Institute of Chemical Technology, Hyderabad, under Dr. J.S. Yadav. After my doctoral research, I got postdoctoral opportunity at McMaster University, Canada. There I got opportunity to work on synthesis of some anti-malarial and anti-cancer drugs. Now I am working as a synthetic organic chemist at Toronto Research Chemicals, Canada, a division of LGC. My primary goal in participating in this seminar is to create interest in young students like you, so that there are much more scientific advancements by you that helps the society. Like all sciences, chemistry has a unique place in our pattern of understanding of the universe. It is the science of molecules. This creation of new molecules has given us new material such as plastic, new dyes to color our clothes, new perfumes to wear, new clothes to color our, new perfumes to wear, new drugs to cure diseases. Chemistry plays a vital role in day-to-day activities. For example, as we are watching this webinar, our eyes are using an organic compound called 11-cis-retinol, which converts visible light into nerve impulses. This morning, if you are happy, it is due to happy chemical called serotonin, 5-hydroxytryptamine. It's a neurotransmitter. The lack of the serotonin causes depression and negative thoughts. When you are walking, doing any kind of physical activities or exercising, your muscles are doing chemical reactions with sugars that gives energy you needed. Not only that, research in chemistry is not just synthesizing medicines to cure diseases, but it is also alert us about future issues. For example, bad coronaviruses in China. For example, the most common words we hear today are corona, COVID, epidemic, and pandemic. It was published in 2019 January by researchers that the SARS, severe acute respiratory syndrome, SARS, MERS-like coronaviruses, is likely to originate, and there is an urgent issue to investigate the detection of signs of such viruses far before this outbreak began. If you type bad coronaviruses in China, you will be able to download the entire publication. The current anti-malarial drug, artemisinin, and their derivatives are not working on people in Cambodia, Vietnam, Thailand, and some Middle East countries. The malaria parasite in their blood has got resistance to present anti-malarial drugs. Present usage anti-malarial drug. The current antibiotics might not work in future, like the old penicillin. There are a lot of research groups in chemistry who are working in these areas. So there is always a growing demand for research in chemistry, and there are a lot of job opportunities that exist in chemistry field. But in research in chemistry, we have to perform the reaction in the laboratory as well as we have to update our knowledge. Now I am going to discuss some of my research journals. Two, de novo synthesis of 2-AP norciclazine, chemoenzymatic synthesis of pestinol, and stereocell 2 synthesis of sanctolide A. Before I go detailed synthetic schemes of de novo synthesis of 2-AP norciclazine, I would like to give a brief introduction about Amyloidaceae family. We see some plants that grows in the rainy season and die when summer arises. Again, in rainy season, they come back to life. Herbaceous perennials are those that die down to the ground each year, but whose roots remains alive and send up new tops to growth in each year. The Hemelidaceae or belong to this herbaceous perennial family. Herbaceous means they never die, their root remains alive in the under the ground. Perennials means they live ever. The Emeraldaceae are the family of herbaceous, mainly perennials and bulbous flowering plants. The Emeraldaceae family contains 73 genera and at least 1600 species. Have you heard about the daffodil flowers and snowflower flowers? These are the daffodil flowers and these are the snow bulb flowers. Both are from Emeraldaceae. Uh, our our research interest is mainly on this isolation and synthesis of narciclazine and their derivative and semi-synthesis of narciclazine derivatives from isolated narciclazine and synthetic narciclazine. These are the bulbs of Amyloidaceae and Galanthus. Both are look same, by we can differentiate by flowers only. These were the molecules of interest from our research group. These alkaloids from this Amyloidaceae has a wide range of biological activities. They have anti-malarial, anti-cancer, display effects on the CNS, and antiviral activities, etc. Now, these are narciclazine. We synthesize this narciclazine and also we isolated this narciclazine from Amyloidaceae, the daffodil bulbs called narciclazine bulbs. After we can after reduce this double bond, it gives the dihydronarciclazine. It has highly potent anti-cancer drug. And also this narciprimine is the display effects on the CNS. The hamanthamine also same. These are the bulbus for the we isolated this narciclazine from this bulbus of daffodil bulbus. These yellow color flowers are from this daffodil bulbus. The white color flowers are from the galanthus bulbus. We first time we found that the existence of 2-AP narciclazine in galanthus bulbus. After plant grows from this bulbus, these are the bulbus for the narciclazine. After the plant grows from this bulbus, the yellow color tips contain 2-AP hamanthamine. We got these are the tips for these bulbous plants. We isolated this hamanthamine from 23 grams of tips. We isolated 100 milligrams of hamanthamine. This is the narciclazine. We isolated this narciclazine from this bulbus and in good yield than previously reported procedures. And but 2-AP narciclazine is not existed in the narcissus extract, but we found this 2-AP narciclazine in galanthus extract. First, for making this 2-AP narciclazine from isolated narciclazine, first we syndiol, we converted to acetonide by 2,2-dimethoxypropane and paratoluene sulfonic acid catalytic amount. After that, we try to invert this alpha hydroxy to beta hydroxy. The difference between the narciclazine and epinarciclazine is C2 inversion center. In narciclazine, it is alpha hydroxy. In 2-AP narciclazine, the C2 center is beta hydroxy. When we try to invert this alpha hydroxy to beta hydroxy by different Mitsunobu conditions, when I tried with tributyl phosphine with benzoic acid, diethyl dicarboxylate, I ended up with diene compound. But with triphenyl phosphine, diisopropyl dicarboxylate, paranitro-benzoic acid, I ended up with oxidation of alcohol followed by migration of double bond to give stable enamine. Then I tried to deprotect this acetonide with trifluoroacetic acid water. We isolated this naciprimine, which is also a minor constituent in amylase. We anticipated that because of this phenolic hydroxy, due to this phenolic hydroxy, the elimination and oxidation reaction taking place. So we protected as methyl ether. This phenolic hydroxy protected as methyl ether with in situ generated diazomethane from N-nitroso, N-methyl urea and KOH. It is selectively deprototes the phenolic hydroxy, but not cyclohexane alcohols. Then the syndiol we converted it into acetonide by 2,2-dimethoxypropane PTSA, gave 68% of this compound, 68% yield. Then this allylic alcohol, beta alcohol, we oxidized with desmartin pyridine oxidation to give the enone alpha beta unsaturated compound. Initially, we try to reduce this enone with Luce reduction conditions, serine chloride, sodium borohydrate. But in Luce reduction condition, we got 1:1 ratio of beta alcohol and alpha alcohol. When I tried with L-selectride, we got 90% of beta alcohol only. I could separated the minor alpha alcohol by a column purification. Then this acetonide was deprotected with 2 molar HCl solution, followed by the methyl ether was deprotected with in situ generated trimethyl silyl iodide from trimethyl silyl chloride and potassium iodide to give our desired 2AP norciclazine. But it is synthesized from the isolated norciclazine. We also developed the scheme for the synthesis of 2AP norciclazine from commercially available 1,3-dibromobenzene. We got this diol compound from Professor Adlaski, Brock University, Canada. He made this diol compound from 1,3-dibromobenzene with cell fermentation of E. coli bacteria. The syndiol we protected as acetonide with same 2,2-dimethoxypropane. But this divinylic diol compound, this unique compound has 2 vinylic bromine atoms, and 2 hydroxy groups were protected by acetonide. But one bromine favors the nitroso-diol salt reaction, and another bromine also useful for the introduce the aromatic boronic acid moiety here. So this divinylic compound subjected under 4+2 nitroso-diol salt reaction. The nitroso methyl carbamate we in situ generated from N-hydroxy methyl carbamate with sodium pyridate. 4+ reaction between these two compounds gave this oxygen. We isolated this oxygen in 60% yield. Then the vinylic bromine atom is treated coupled with the aromatic group, substituted with the aromatic group by Suzuki-Mayura condition. With palladium tetrakeys, the vinyl bromine atom forms the palladium complex. Then it couples with boronic acid to give the aromatic ring substituted oxygen. Then we selectively reduced the nitrogen-oxygen bond with molybdenum hexacarbonyl. Also result the cleavage of bromine atom. It gives the enone compound. Then we tried here. We reduced this enone with serine chloride 7H2O. We got beta alcohol as the major product. We separated this beta alcohol. Then this acid level group is hydrolyzed with HCl, then acetylation with acetic anhydride to give this intermediate. Our aim is to form the lactam here. So this triestate compound under Bristler-Neplasky condition with cyclic anhydride DMAP in DCM, we got 31% of this lactam. Then the methyl ether was selectively decoated with TMS chloride, trimethyl silyl chloride, potassium iodide. Then acetate hydrolysis with K2CO3 methanol to give the 2AP norciclazine in good yield. Next, chemoenzymatic synthesis of antifungal compound pestinol. In the literature, we can see this is the iene-diene fragments. We saw many natural products which has this type of iene-diene chemistry as not explored, and they have more biological properties like antifungal, antiviral, antibacterial. So our intention is to explore this iene-diene chemistry. So we choose this spesnol to explore that ion-diene chemistry. But in the literature, we can see this diene chemistry is well explored. I forgot to share here some diene chemistry molecule, but this is the ion-diene chemistry molecule. Or we also prepared some endoquinone. Instead of this tetrol ring, we prepared some endoquinone and we coupled to this triple bond, this ion-diene fragment. Those are under screening. For making the first phenol, the first discussion is that the triple bond and vinyl bromide both were coupled with Shonagashara coupling. We made this triple bond ion-diene fragment from the general bromide, and also this tetrol fragment we made from the bromobenzene. For making this general bromide, we started the scheme with commercially available general. For making this general stone, we started with the general bromide. We treated with ethyl acetate in K2CO3 stone to give beta hydroxy compound. The beta hydroxy compound is saponification with KOH methanol to give general stone in 65% yield. Then this general stone, we treated with the LDA. LDA in the institute generated LDA from diisopropylamine and n-butyllithium. It gives the kinetic product, less substituted enol. The unstable less substituted enol is converted into triplamide by using this triplamide. Thus, this kinetic product, triplet enol is coupled with the TMS acetylene by Shonagashara condition. Shonagashara condition is the formation of CC bond between the vinyl or vinyl triplets with alkynes. So this triplet enol is treated with palladium dichloride bistriphenyl phosphine copper iodide diisopropylamine as the base with TMS acetylene to give this ion-diene fragment. The trimethyl silyl group is hydrolyzed with K2CO3 methanol to give fragment A to give low boiling ion-diene fragment. Fragment A is in our hand. Next, we want to make fragment B for the bromobenzene. We got this diol from the Sadlaski group, Brock University. We have collaboration with them. They have some equipments to prepare this cell culture and cell fermentation equipment. We got diol from that Adlaski, Brock University, Canada, and this diol was converted as acetonide by using same 2,2-dimethoxypropane PTSA. Then this double bond, the isolated double bond was oxidized to syndiol with osmium tetroxide and NMO. Then fragment A and fragment B we try to couple we use different Shonagashara conditions to couple fragment A and fragment B, but none of the reaction worked. We thought because of high polarity difference between the fragment A and this fragment A means this is a hydrocarbon chain, non-polar, it's soluble in hydrocarbon non-polar solvent, and fragment B is the polar compound, it's soluble in methanol, polar protic solvents and polar solvent. So we thought maybe polarity difference, because of polarity difference none of the reaction working, so we changed it to the solvents to piperidine benzene 1:1 ratio. We could see the product formation observed, but yield very less. The fragment B is not completing on TLC. So we screened many palladium catalysts for Shonagashara condition.
Hello.
Finally,
Sir, your slides are not visible.
It is visible, sir. Please speak.
No.
It is visible, sir. Slide is okay, sir. Dr. Bora, please carry on, sir.
okay, sure.
Madam, sir, slide is visible, but it is not on a full screen. So, if possible on a full screen, then we are seen properly.
It's in full screen mode.
But sir, it is full screen. Mr. Bora, is it in the full screen?
Yes,
I think
it is in full screen mode.
Yes. Yes, sir. Please carry on, sir. It is in full screen.
One will have to just delete the chat box,
Pin.
then it will be in full screen, and pin it.
Sir, pin it, sir. Sir, Dr. Bora, please carry on, sir.
Okay, thank you. The fragment A and fragment B in our hand, we try to couple these two fragments with Shonagashara coupling condition. Finally, we achieved this Shonagashara coupling with palladium dichloride bisacetonitrel copper iodide as a catalyst and piperidine benzene solvent. 72% yield. We got this fragment. Then we hydrolyzed this cyanide with acetic acid water. We got desired pestnol, which is our molecule of interest. This is the first total synthesis, and also we confirmed the stereochemistry of this tetrol chemistry, and also this specific rotation exactly matching with isolated natural product. The third is steroid cell to total synthesis of marine macrolide sanctolide A. This is also my first total synthesis, and also I confirmed this methyl center. In isolation paper, they didn't confirm the methyl center. We confirmed it is the methyl, it is the beta methyl. Sanctolide A is a 14-membered polyketide non-ribosomal peptide. In this moiety has N-methylenamide moiety and 2-hydroxy isovaleric acid functionality are embedded in this macrolide. It has a CNS active molecule. For the making this molecule, the first disconnection is a enamide double bond. We made this enamide double bond by dehydrative cyclization from aldehyde and amide. Then these two fragments we coupled with Yamaguchi esterification. Then we got this alcohol from this propagylic ketone by Naiori Esmetic keto reduction condition. And also we made fragment B from commercially available 2-hydroxy isovaleric acid. For making the fragment A, we started with hexanol as the starting material. We know here I used Keck-Morocco condition. The difference between this is the allylation of aldehydes to homoallylic alcohols is called Keck allylation. The difference between the Keck allylation and Keck-Morocco allylation is we use the along with the tributyl tin hydrate, titanium tetrachloride, titanium isopropoxide, we use silver oxide and binol. With this, it gives the titanium 4 complex. It not allows the rotation of oxygen titanium bond. So it completely blocked the one phase. So we got with hexanol with allyl tributyl stannane in Keck-Morocco allylation. I got 95% enantiomeric excess of required propagylic alcohol by Keck-Morocco condition. Then this secondary alcohol I converted to methyl ether with sodium iodide, methyl iodide in THF. Then this double bond is hydrolyzed with osmine tetroxide NMO acetone water 1:1 condition. It gave diol compound. Then this diol compound I chopped with sodium peroxide THF water. It gave aldehyde compound, terminal aldehyde with 1 carbon decrease. Then the aldehyde treated with this acetylene. I made this triple bond, the acetylene from the Roche ester. This is a literature procedure, so I didn't describe about the scheme of this making this fragment. I treated this acetylene with n-butyl lithium to give acetylide. Then nucleophilic addition of this acetylide to this aldehyde. Aldehyde gave the diastereomeric ratio of 2 alcohols, beta alcohol and alpha alcohol. This time we don't know which is our required alcohol. According to discussion approach, required alcohol is beta alcohol. So we don't know which we got the 40:60 ratio of all beta alcohol, beta propagyl alcohol and alpha propagyl alcohol. I don't know which is beta alcohol. So I took small quantity from this mixture. I oxidized to keto. Then I subjected that keto compound in Naiori Esmetic reduction. The best advantage in the Naiori Esmetic reduction is when we use in propagylic ketone, when we use RR Naiori catalyst, it gives R alcohol, R propagylic alcohol. When we use SS Naiori catalyst, we will get S propagylic alcohol. So based on that, when I need beta alcohol, so I use S propagyl R propagylic alcohol. I use RR Naiori catalyst. I got this propagyl alcohol. So I matched it with TLC. The minor compound 40% is my desired propagyl alcohol. So the undesired beta propagylic alcohol I oxidized with desmartin pyridinane. Then this propagylic ketone subjected with same again Naiori Esmetic condition with RR Naiori catalyst parasamine ruthenium chloride, formic acid triethylamine to give this propagyl alcohol with 99.3% diastereomeric excess. Then I try to saturate. saturate this triple bond to single bond with normal palladium carbon and methanol, ethyl acetate, nitrogen gas, balloon pressure. But when I tried this reaction, the reaction ended up with 80% required compound along this 20% oxidized product. This is also reported in the literature. So same reaction I repeated in high dilution condition in H cube apparatus. H cube is a type of flow reactor. In high dilution condition, I could see single. I could isolated required compound as major. Then fragment A is synthesized. So for making fragment B, I started with all of isovaleric acid. The acid group was selectively protected with L bromide with K2CO3 DMF. Then we formed the ester again with this 4 benzoxy benzoic butyric acid we made from the 1,4-butane diol. This acid and alcohol is coupled with the DCC DMAP condition. I got this ester. Here 2 esters competition. One is ester, another is the allylic ester. Allylic ester. We selectively deprotected the allylic ester with palladium tetrakis, triphenyl phosphine, morpholine. We got this acid compound without disturbing this ester. So fragment A and fragment B we have in our hand. So we couple these two fragments by Yamaguchi esterification conditions by using 2,4,6 trichlorobenzyl chloride, diisopropyl ethylamine, DMAP, toluene. First, the acid gives the anhydride with this 2,4,6 trichlorobenzyl chloride followed by alcohol addition to give this ester. Then the TB-DPS ether selectively deprotected with tetrabutyl ammonium fluoride to give this primary alcohol. Then our aim is to convert this primary alcohol to amide. Then benzyl ether to aldehyde. So first we deprotected this TB-DPS ether with TBAF. Then this alcohol we convert into acid by 2-step sequence. First alcohol we oxidize to, we can convert in single step. But here the methyl center is when I use tempo BIB in more equivalents, I can get the acid with the methyl. But I could see the inversion at methyl center also. So firstly, I choose to oxidize the desmartin paradenine because desmartin paradenine is ST condition. So it's oxidized to aldehyde first. Then this aldehyde I converted into acid by Kinney cross oxidation by using sodium chloride, sodium dihydrogen phosphate, 2-methyl-2-butene as a scavenger, and tetrabutyl water. I got acid without inversion of this methyl center. Then this acid converted into methylamide by mixed anhydride method by using ethyl chloroformate, triethylamine, and aqueous methylamine solution. We got quantitative amount of this secondary amide from this acid. For making this amide, this is the best method in aqueous medium. Then this benzyl ether is deprotected with palladium carbon, hydrogen gas. We got this primary alcohol. Then this alcohol oxidized to aldehyde with desmartin paradenine oxidation. Then the aldehyde and a secondary amide we have. Both are we heated in trifluoroacetic acid benzene by oxidative elimination. First it forms the aldehyde, amide attack on the aldehyde, form an elimination of double bond, then the migration of double bond to form the stable enamide to give sanctylide. And also the specific rotation of the our specific rotation of this natural sanctylide, synthetic sanctylide A is exactly matching with isolated sanctylide A. So here for making this molecule we use Kekmora calculation. We confirmed the methyl. First time we confirmed the stereochemistry of methyl center. This is the isolated NMR of isolated natural compound sanctylide A. This is the synthetic compound sanctylide A. Thank you all. This is all my PhD postdoc career molecular sensei. All these. Thank you. I acknowledge Dr. J.S. Yadav, Dr. P. Srihari, CSIR for financial assistance, ACSIR, Dr. Jim McNulty, my postdoc supervisor, Dr. Dhruva Chakravarti, and BN College, and webinar attendees. Thank you once again. Questions? Any questions?
Thank you, sir, for your nice presentation. Actually, in the chat box, we have not found any questions regarding your presentation, but I want to request you that as most of the participants are doing, they are BSc and MSc students, so I therefore request you to say some words how to proceed in the field of research in chemistry.
Field of research in chemistry is a very wide topic, but I worked in natural product synthesis. Some research groups working on methodologies. My best advice is after masters, I am they want to do the research in abroad or what research field, whatever the research field.
Hello.
Hello.
Please give any idea about how to proceed in the field of research if they want to do.
Okay.
From your experiences.
Oh, from my experience, during their masters, in the second year onwards, some standard textbooks, some research journal, if they see, or for in the PG colleges, degree colleges, our faculty members teach rearrangements, named reactions. Just that time we can understand and we can memorize and we can write. But people, if they find some journals, some natural product synthesis journals, directly we use. For example, for making some drugs, brevostatin, some the total synthesis starting. They use all types of reagents, all types of rearrangement. The PG student especially, if they try to understand the conversions, they can easily understood the mechanisms, as well as they can increase they memorize that named reactions, and they can that is very useful. For research in chemistry is very good. Very good means some people like the research in chemistry. Some people simply they disconnect after MS. Both are fine. Depends on the person to person. It depends on person to person. And also,
thank you, sir.
After that master, in India for doing PhD, CSR is compulsory. They need to qualify CSR exam. But not only in organic chemistry, not only that. After masters, if they're not qualified CSR also, better to join any research institute for the projects. They can learn they can get the hands-on experience from that projects, and also after 1 year, 2 years, they can publish the journals. And as if they want to interest, they can continue PhD. Otherwise, if they want to come abroad, based on that research journals, based on that research institute experience, they can apply to abroad like North American continent. The professor will accept easily for the for PhD for those candidates who have experience in India. Many people are coming like that only here.
Okay, thank you, sir. Can you share your journey, especially?
Pardon, I am not audible here. Pardon?
Can you share with us your journey?
Oh, my journey.
Particularly, yes, sir.
Yes. After my masters, I don't know about CSR. That 2005, I don't know about CSR exam because I studied in Andhra University. Then I'm looking for the job. I joined first at Milan Laboratories. I worked 3 years, but I didn't get any satisfaction. Then I moved to Jubilant Chemicals Limited, Noida. That's a CRO company. I like that work culture, but I realized that PhD is important to grow up in my career. Then again I came back. I prepared for the CSR exam for 3 months. Then I qualified. I got the 67th rank in CSIR. I qualified GATE. Then I got opportunity to work on Dr. J.S. Yadav IACT. Then I started my PhD. Before I start my PhD career, I thought maybe organic chemistry, I have good industrial experience, so I can complete my PhD in 2 years, 3 years. But that is not easy. Industry experience is completely different than research experience. Then I realized it. We have to read a lot of journals. We have to improve the knowledge. We have to So for my PhD takes 6.5 years to complete. During the writing my thesis, I got postdoctoral. I got the 3 postdoctoral opportunities, but I choose to come to Canada because Canada is a nice place to start my career. So then I came. I choose to come Canada for postdoctoral research at McMaster University under Professor Jim McNulty group. Then I worked 3 years under him. During that, I got permanent residence in Canada. So I applied for the jobs. I got job at Toronto Research Chemicals. This is my experience.
Malavika, please unmute yourself. Please unmute yourself, Malavika. Malavika, unmute yourself.
Okay. Can you hear me now?
Yes,
My
yes.
best, can I say some opinion, my suggestions to people who are in the MS?
Yes, yes, you can say.
My best suggestion is after their masters, um, better to join any research institutes or some some industries. They will get good knowledge, hands-on knowledge. If they work in the research institutes, they will get good knowledge with faculty members and senior student. After 1 year, 2 years, if they want to, if they wish to continue PhD, they can continue. Otherwise, they want to do the PhD graduation abroad. Better to apply the professors in North American continent. They simply accepting people who has experience in India, especially from research institutes, and they can come. And also they are giving stipend to those people. They can easily survive for 5 years, 3 years to 3 years, 4 years for completing PhD. This is my best advice.
Okay, thank you, sir. So
Thank
we
you.
will pick one question from the chat box.
Okay.
Nisa Garg is asking, she is, my research work got registered for herbal drug on COVID-19. How can I apply it Ayush Bibhag for trial?
No, I'm no voice breaking. Can I?
Okay, I am repeating the
Can you?
question.
Yeah.
Nisa Garg is asking, my research work got registered for herbal drug on COVID-19. How can I
Okay.
apply it Ayush Bibhag for trial?
Aish Vibhag for India in India?
Yes, sir.
No, I don't know how to apply.
Okay, sir. You have no idea?
No, I have no idea.
Okay.
Because better to choose any host in any institute. Uh, because independent research, we have to choose host is important in India. If she choose any host means any professor in any institute, they will accept her, and she can start research under him. They will supply, they will provide all those things what she needed.
Okay. Thank you, sir, for your nice presentation. And I would like to thank you from bottom of my heart for giving us your valuable time and join us in this international webinar. Thank you so much, sir.
Thank you very much for BN College and all people who are webinars attendants. Thank you very much.
Thank you,
It's my
sir.
pleasure.
Goodbye. Now, I'm going to introduce our second speaker for this webinar, Dr. Beverages sir. She is currently working as professor and head in PG Department of Chemistry, Madhav Science Postgraduate College, Ujjain in Madhya Pradesh. He is presently also a member of, he is presently working as a president of Association of Chemistry Teachers, Homi Bhabha Center for Science Education, TIFR Mumbai also. So, in addition to MSc, MPhil, PhD, and PDF in University of Durban, Westville, South Africa, Sir has an experience of teaching of more about 33 years. So he has more than 70 research publications in various reputed national and international journals. He has produced till now 18 PhDs, and several students are still working under his guidance. He is also an IUPAC UNESCO member nominated by INSA. His research interests includes science education, green technologies such as nano-zero-valent iron particles for mineralization and degradation of organic pollutants and dyes, photocatalytic degradation of organic pollutants. He is the referee for several referred journals such as Journal of Physical Chemistry by ACS, Journal of Hazardous Materials by Elsevier, Journal of Indian Chemical Society, etc. He is a member of several chemical associations. So today he is delivering lecture on exploring the scientific processes through the discovery of oxygen by Joseph Priestley. So I would like to invite Dr. Paresar. So please deliver his speech. Over to you, Paresar. Please unmute yourself, sir. Please unmute yourself, Paresar.
Yeah, okay. So I'm audible now.
Yes, sir. Yes, sir.
Thank you very much. And thank you, Principal of BN College, Head of the Department, the Chemistry, Dhobri College, BN Dhobri College, and the convener, Malabika Bora ma'am. So it's a great pleasure. And it was really a pleasure listening Dr. Bora, just now before me. And one good thing, which really I'm very happy to look at it,
Sir, you again got muted. Sir, you again got muted. Yeah.
Yeah. So it is okay now, I think. So
Yes,
I mean, it's a great pleasure, the most of the attendees are students, and what I'm going to speak today, that is, it is shared. It is
Yes,
shared.
yes.
I mean, can you see it on the full screen? Because I was unable to see Dr. Bora's presentation on full screen. So before I go ahead, I want to ensure that my presentation is there on the full screen. Who is going to ensure it? Malabika, Dr. Malabika?
Yes, sir.
It is there on the screen, full screen?
No, it's not coming, sir.
It is not coming. Then just wait 1 minute. I have to just again do it. I'm just sharing it again. So you have to just ensure that my presentation is there on the full screen.
Okay, sir.
Just wait. It is sharing.
Vijit, are you there?
Is it there? It is sharing?
Yes, sir.
No, sir.
But I cannot see my screen from this side. I have to check. Just wait. It says
Sir, your screen is sharing. Your video is sharing. You just minimize your video and start your presentation, sir.
Okay, just 1 minute.
Just minimize the screen. All right. Now just start the presentation. PPT. Again, sir. Minimize.
Okay. Yeah. Just 1 minute. So now it is visible?
Yes.
Yes.
Yes, sir.
Okay. Thank you very much. So I will just go for the slide. It is better now.
All right, sir.
It is better. It is on the full screen.
Yeah. Yes. It is on the full
Yes,
screen.
sir.
Okay. Thank you very much. So, just exploring the scientific process through discovery of oxygen by Joseph Priestley. I'm so happy to talk, and this talk is particularly for the young students, those who are keen to carry out the research in the coming years. So let us see, how even in the olden times, the person like Joseph Priestley, somewhere around 1774, he did a lot of research, using all small apparatuses designed by his own. So we'll just explore it, what were the difficulties and how the difficulties were overcome by the scientific process. So let us come with me and see 400 BC, that is almost 2005 years ago. the Greek philosophers, they used to say that the earth, water, air, and fire, these four were termed as the elemental components of the whole creation. So that was the concept, which persisted in the scientific world for more than 2005 years ago, such a long ago. Just try to understand. I mean, like these days, when the knowledge is doubling, so quickly. But this particular information that air was one of the element, and it persisted for so many years. And the credit goes to Priestley and various, the British scientists, somewhere around 1700. They dispel this idea that air is an elemental form. So just we'll see, I'll go just storyline, how it went all the way. So this is Priestley, Joseph Priestley, we all know. And the Priestley dethroned an idea that dominated science for 23 centuries, 2,300 years. And what was that? That air was an element. So somewhere in 1774, Priestley found that air is not an elementary substance, but a mixture of gases. And later on, and it was this colorless and highly reactive gas, which he called dephlogisticated air, and it was named oxygen. So see, this is a, we are on a webinar, and most of the students, they are muted. If suppose you had not been muted, definitely I would ask, that who named this dephlogisticated air the name oxygen. So probably some of you definitely may be aware of it. It was Lavoisier from France who named this dephlogisticated air as oxygen for the first time. And the Joseph Priestley was a British scientist. We need to understand, like those who have a scientific temperament, how they get inculcated their interest from different, the applications side, or from the surrounding itself, which is surrounding. So this, the Priestley was working. He was a minister. He was in the part of a ministry, and there was a brewery, located close to his office. So when he saw that the carbon dioxide coming from because of the fermentation, the bubbles and effervescence coming out of the substance, so he got interested because of that, and what he thought, like he found a way to introduce this to produce artificially what occurred naturally in beer and champagne. So water containing the effervescence of carbon dioxide. So let us see, later on in the beer and in like in Coca-Cola kind of thing, all the cold beverages, it is the artificially generated carbon dioxide. So this was the idea given by Priestley. It looks to be small, but let us think, if suppose there is no something like the artificial carbon dioxide, so there would not be any Coca-Cola kind of thing and all that. So this effervescence coming out of fermentation, during the brewing, inculcate interest in working of gases. That was the beginning. How Priestley got interested into working for gases. Although gases is a new word, in those times, they used to call only airs. Just try to understand, various gases were named only airs. One more thing about Priestley, because we are talking about Priestley, he gave one more important thing, that is we use, the rubber erasers. Yeah. So the credit goes to Priestley for that also. So for brewing kind of thing and for eraser. So whenever I talk and we just when we say that it was Priestley who discovered oxygen. So I ask my younger students many times, when I'm talking to them in a physical format, that I wonder how people breathe before Priestley discovered the oxygen back in 1774. It is not 1772. It is 1774. So it's very, very, very bizarre and very odd kind of question. That what people were doing before Priestley discovered oxygen. So it's just in a lighter manner. The oxygen was there, only it was discovered, it was known that it is a part of one of the components of air. So that is how thing goes. Now, the early beliefs about air, nobody knew what air was. See, air was supposed to be an element for 2005 years. And what we are talking about, something about 17. So in those days, the most pressing issue in chemistry and of course physics was to determine exactly what happens when anything burns. That was something very important, and nobody knew, that what is the burning. So we will just go down to the memory lane, and see what was the concept in the scientific world about the burning. Whenever the combustion takes place, what happens? So there was a phlogiston theory, and what was the theory says? The theory says.
Sir, you again become muted, sir. Pari, sir. Pari, sir. You again become muted, sir. Pari, sir. Excuse me, sir.
Yeah, it's okay now. It's okay.
Yes, sir. Yes, sir.
It's okay. It's okay now. You can hear me
Yes,
now.
sir. Thank you, sir.
Thank you. So now what I was telling about the phlogiston theory for burning of substances. So theory says that every substance that burns or which can burn has phlogiston in it. And whenever the burning takes place, that particular phlogiston comes out of that substance. So that was the phlogiston theory that really persisted for a very long time. Okay. The theory held that when a candle burned, phlogiston was transferred from it to the surrounding air. And when the air became saturated with phlogiston and could contain no more phlogiston, the flame went out. That was the theory of burning. I mean, it looks ridiculous at the moment, but see how the knowledge advances. That is what we need to understand in today's talk with me, to talk with you. More so, even the breathing, the scientists were aware of the breathing, and they were of the view the same. Whenever we breathe out something, the phlogiston comes out of our body. That was the theory of phlogiston. And a typical test for the presence of phlogiston was to place a mouse in a container and measure how long it lived. I mean, in a container when there is no air going inside or coming out. When the air in the container could accept no more phlogiston, the mouse would die. And many experiments were carried out by Priestley, and he was really, there were many jokes of that time, that the mouse were really worried because of Priestley, because he was carried out so many experiments on mouse, and because of that, so many mouse died. But anyway, that was the process how they were trying to understand about the air. I'm trying to run this small experiment. Let us see if it works. Just wait.
Joseph.
Hello, sir.
Yeah, it is audible.
Yes, sir, but it is not full screen.
What happened?
It's not coming full screen.
It is not coming fully. Okay,
Yes.
I'm leaving it. I'm going ahead. Don't worry. You can't see it.
Yes, sir, we are seeing, but not in full screen.
Okay. No problem. It is not in
Sir,
full screen. I'm very sorry. Just wait.
Okay, sir.
Just slideshow and yeah. Is it okay?
Okay, sir.
So anyway, I'm leaving it. That experiment is all known to us. The mouse kept in a container, and when the whole of the phlogiston, that was the theory says, comes out, and after that, the mouse died. So what were the observations made by Priestley out of that small experiment? So Priestley made enormously important observation. A flame would extinguish, goes off, and a mouse would suffocate when placed in a sealed jar. However, putting a green plant in the jar, you may be knowing about that experiment where, the Priestley put one small plant inside the jar, and the mouse was there also inside that. And exposing it to the sunlight would refresh the air permitting the flame to burn and mouse to breathe. I mean, see, when a plant was also kept inside the container, the closed container where the mouse was there, what was the observation? When it was placed in open sunlight, because of what? Because of the photosynthesis. So photosynthesis, that means the plant giving the more oxygen inside, and because of that, the mouse which was dying earlier, he lasted for longer. So somehow, they were trying to understand all these kind of things. So that was the photosynthesis. So Priestley wrote, the injury which is continually done by such a large number of animals, in part at least, repaired by the vegetable creation. See, he was also worried because when he was working to know about, how, the respiration takes place, how the burning takes place and everything, lot of, the mice were, they died. So that was a kind of a small, thing, he said that because of the photosynthesis, oxygen, some kind of thing is coming out, which is supporting the life. Thus he observed that the plants release oxygen into the air, and we all know that it is photosynthesis. Anyway, I want to tell you the whole of the thing, which you're trying to explore, that is all the British scientists, how they were doing, they're trying to know about the various kinds of gases. So one person, Joseph Black, in somewhere 1754, that is almost 20 years before the oxygen was discovered by Priestley. Yeah, 1774 was the year when the oxygen was discovered. So almost 20 years prior to that, it was Joseph Black. He identified one type of gas, but they call it air. I'm telling you that the gas was not there. They were just trying to say air, and the name was fixed air. Why? And what we call the fixed air today? We call it carbon dioxide. And why they call carbon dioxide fixed air in those days? Why the Joseph Black called it fixed air? Because it could be returned or fixed into the sort of solids from which it was produced. Okay, like, for example, magnesium carbonate, when it was heated, giving carbon dioxide. So what it was thought that when magnesium oxide, from the magnesium oxide, you can again get magnesium carbonate. So that was the name fixed air. So that was what we call carbon dioxide. Similarly, it was Henry Cavendish, 1766. He produced another gas, he isolated, and that is known as flammable air. And the gas which Lavoisier would name hydrogen, from the Greek word from the water maker. So I'm showing you that how these people, from Britain, they were working on different types of gas. Then 1772, it was Rutherford. It is not that that atomic structure Rutherford. It was a different Rutherford. It's a Daniel Rutherford. He identified fixed air, and he called it noxious air. So what we call a noxious air today, because it asphyxiates mice placed in it, in the container, and we call it nitrogen. Today we call it nitrogen. So these are the three things that I showed you. That Joseph Black, who came out with the fixed air, that is carbon dioxide. Then Henry Cavendish, that is flammable air, that is what we call today hydrogen. It was named by Lavoisier. Then Rutherford, he came out with nitrogen. Anyway, so now let us come up again with Priestley's investigation, because now we have come up to 1772. Priestley was already working on it, on various things. Now he systematically analyzed the properties of different airs. Again, see, different airs using a very simple apparatus. You might have seen this, the pneumatics, like how to collect gas over water or mercury. That was very important, and just to calculate the volume. So these were the small apparatuses which were used by these scientists of that time, And let me tell you, it was the period 1770 when chemistry was not considered as a separate subject. Although physics was established by the time because of the Newton's laws and all that, but chemistry was not considered as a separate subject, and not sophisticated instruments were there. But these scientists were working with these all small kind of things, and they worked out. Priestley called his discovery dephlogisticated air, that it supported combustion so well because it had no phlogiston in it. Again, everybody of that time, even let me tell you, all the scientists, even Priestley, Lavoisier Lavoisier is considered to be as a father of modern chemistry. He was from France, and he was of the view of they all were talking in terms of phlogiston theory. Although Lavoisier and Priestley together, in a collaboration study, they dispelled this theory later on. But by this time, when he was working, the air, he was calling the oxygen, he was calling dephlogisticated air because it supports combustion so well. Hence, it could absorb the why. And see, what was the point in that? Why this dephlogisticated air, which today we call oxygen, supports combustion? Because it could absorb the maximum amount during the burning. Again, the same theory, phlogiston theory. If something burns, a material which is contained by the flammable substance, it comes out of that. And if one particular gas supporting the combustion, it is because it is absorbing the maximum amount of this kind of thing. So they were at that time, they were thinking in terms of phlogiston theory only. This is something very important, and this picture is also very important, where Priestley trying to generate oxygen. So just by taking a 12-inch wide lens, see the lens, and he focused sunlight on a lump of mercuric oxide in an inverted glass container placed in a pool of mercury, and the colorless, odorless, and tasteless gas emitted from the lump caused a flame to burn intensely and kept a mouse alive about 4 times as longer as a similar quantity of air. These two things. So that was a very important and very breakthrough in the history of the gases and all. Like for the first time, the oxygen. Although by this time also the name was not given oxygen; it was given Lavoisier by Lavoisier later on. But this is how one particular a dephlogisticated air, what the Priestley used to call it, and that was generated. And it has two properties: one, it is supporting the combustion. And secondly, the supporting the life also, and the mouse was found to alive for more time, 4 to 5 times longer than in its absence. Just see how these people, working in those days using the very, very, small and the self-made indigenous apparatus, separating the gases and generating the gases just by taking small cylinder and putting into the mercury and collecting the gases and all that. One more thing, that Priestley did when he generated this dephlogisticated air, or sometimes it is known as the Priestley's air, what we call it a oxygen. When he generated it, he himself breathed it. See the beauty, the breathing of that particular gas by Priestley himself, and how he reacted when he did that. So that is the thing. What he said, the feeling of it in my lungs when he breathed it. No, the feeling of it in my lungs was not sensibly different from that of common air, but I fancied that my breast felt peculiarly light and easy for some time afterwards. Who can tell? But that in time this pure air may become a fashionable article in luxury. Hitherto, only 2 mice and myself have had the privilege to breathe it. That was the thing. It was the pure oxygen. We know when the pure oxygen is breathed, certainly you will feel very light and quite good, So that was his feeling, He was so happy with that he found that something he got, something he could separate, and generate it, which really helps, better. The chemical revolution, let me tell you guys, you are mostly students, I'm addressing really to the students and trying to tell them, that how the scientists of each time, they work and how they are really, really analytical in their approach. And so the word chemical revolution, it was given by Lavoisier. If just recall, we are talking about 1770, 1774, 1780, and it was the time when French Revolution was going on in France. Similarly, the American Revolution was also going on. So 2 revolutions were going on. And Lavoisier said that the 3rd revolution that he called a chemical revolution, where they could just come out with various kind of things, like the oxygen was discovered, various gases were discovered. They came to know about the burning, that how the burning takes place and everything like that. So shortly after his discovery, Priestley visited France. He was from England and he visited France and he met Lavoisier, the father of modern chemistry, and they discussed there, and Lavoisier was also, working on combustion, that how combustion takes place, what is the science behind combustion, and this particular finding by Priestley that when the mercuric oxide was decomposed using the light and the gas generated, what was helping the combustion, this particular information really changed the whole of the things. I'm not going into the details of that, but Lavoisier just got hold of this particular concept and he worked on that, and then the whole phlogiston theory was dispelled, it was removed, and the Lavoisier then came out with the idea that it is this particular, he said it is Priestley's gas or Priestley's air, that is supporting the combustion, and that we all know today that oxygen is now combined whenever the combustion takes place. So dephlogisticated air was the clue Lavoisier needed to develop his theory of chemical reactions. And that is what he called the revolution in chemistry that would finally dispel the phlogiston theory. So that is the beauty of collaboration. In science, collaboration is very important. Priestley was working in England with his old small apparatus and everything. Lavoisier was working in France. When they met, when they had a collaboration and they come out with a wonderful idea about the combustion, the theory behind combustion. Okay, Priestley's gas. The burning substances, Lavoisier argued, did not give off phlogiston. Phlogiston theory was dispelled. It was removed. Okay, what he said, they took on Priestley's gas. It was the statement from Lavoisier that the Priestley's gas supports combustion, and Lavoisier called oxygen from a Greek word, like acid maker. So first time the Priestley's gas was named, and what the Priestley used to call it a dephlogisticated air as the oxygen. Guys, let me tell you, as I told you, that I'm really speaking to the students for various classes, like how this Priestley was a very genuinely intelligent guy, let me tell you, usually what we think, whenever we think of a chemist or a scientist, we always think, he must be a very focused guy. Definitely they are there, but everybody may not be there, they are quite multi-dimensional many times. They have different varied interests in different fields, but at the same time, you can be a good scientist. This is the Priestley is a wonderful example of this kind of thing. So see, he was very good at Latin, Greek. I'm talking about the languages. The Priestley knew Latin, Greek, French, Italian, German, and the smattering Middle Eastern language also. And he was good at mathematics also. He was a very good philosopher also. And see, in those days, what was the specialty with Priestley, that he was a very good priest. You're getting my point. He was a priest. And at the same time, he was a very good politician also. I will let you know, the result of his interest in politics. But anyway, he was a priest, he was a politician, and at the same time, he was a wonderful scientist. As I shown you, like about the carbon dioxide and the beverages, kind of thing, and then the eraser, and then the discovery of oxygen, and many more things he has done, in the field of science. But see, what happened, because of his differences with the Church of England of that time, and he was a religious man, but the idea of religion was different from him, and his church was different, So because of that, he was not given admission in Oxford and Cambridge, but anyway, he suffered and he studied in some different university, and so that shows, like if suppose you are not given an admission in the best of the universities, still, you can do much better, like the Priestley did. So, and because of the religious belief and his the political things, he was suffered a lot. Like anyway, this I already discussed with you. Like he had been to France, and because of his collaboration with Lavoisier, and collaboration took place, and the phlogiston theory was kicked out, and they all came to know about the the combustion. So my point of view, like, like what happened, this fellow Priestley, he did a lot of science also, but at the same time he was a priest, and he was, I mean, he was just, even the political views did not match with the political policy of England. So he was removed from England, and then he went to US. He settled there, and this is how, he was a rebel. So what I say, sometimes it is good to be a rebel also. And when he left England, his house was burned. So this is how things happen. You never know. You are such a good scientist, but at the same time, if you have something extra, something you have to face and you have to suffer. So anyway, my whole thing was that Priestley has really contributed enormously despite all the shortcomings, and his collaboration with the Lavoisier, the best the chemist of that time. They could come out with various kind of things, and the discovery of oxygen is the biggest thing. That is, the credit goes to Priestley. So thank you very much. That is what I wanted to speak to you today, that how the scientific explorations are done using all these kinds of things and just by collaboration. Thank you very much.
Thank you, sir, for such a nice presentation and wonderful. It was wonderful to hear you. It was great. Actually, we have no questions in the chat box, but I want to request you to please, if you can, show us the video of the experiment.
Video of the
experiment?
Yeah, please speak again.
You have included one video in your presentation.
Yeah.
That video, if you can play it now.
Should I run or should I play? Okay.
Yes, sir.
Okay.
Thank you, sir.
Okay,
Sir,
okay, yeah.
one of the participants is asking,
Yeah.
Swedish Bharadwaj, how can we achieve the exposure to higher research in chemistry after BSc?
Sorry, once again, please.
How can we achieve the exposure to higher research in chemistry after BSc?
After BSc?
Yes, sir.
See, yeah, no, after BSc, like in India, no, like we don't have a research facility after BSc, but in Europe and in US, no, they have a provision for undergraduate research, which really we don't have in India much. So at least, I mean, either, after having done 12th, if somebody is interested in research, so he or she can go to IISER. No, IISERs are very good institutes in India if you want to do it in India. But if suppose you are doing BSc, then definitely you have to go for a master's course, MSc, and then you can just by entering into various exams for IIT or even for ISER and these kind of things. So even you can go to ISER after 12th, but since you are asking that you are doing BSc, then you have to do your MSc and then you have to appear for the NET examination. And just once you get an examination clear, you can go into any of the premier institute of India. Yeah, that is the possibility. But if you want to go overseas, that is a different thing. Yeah.
Okay, thank you, sir. So can you add something for any comments for the students who are watching?
Yeah, definitely. It is always a pleasure, like scientific temperament. See, the observations, whatever we see, like in science, you need to have good observations. That is one thing. And certainly, like there are many serendipities you may be aware. Like whenever you are working on some particular thing, but if you are very much aware of the deviated results, which are not expected results. So if you are quite aware of it and you are ready to address to those results, so you can get some very good results, like in the form of serendipitous research. But at the same time, you need to understand, your own capability, your own temperament. If really you are inquisitive, if really you want, see, like in chemistry, one of the things is a synthesis. I always interested in synthesis, because synthesis is something, like where you can produce a material or a substance which was never ever present on this planet. So chemistry gives you an opportunity. If you are interested in a kind of an organic synthesis or any kind of other, this is the age of material science, and you can design material of various uses. So, yeah, that is good. If somebody is interested in research, so you should really pursue it, and that is really good.
Thank you, sir. So one more request to you. Can you say something, some motivational words in this pandemic situation for the students?
Yeah, that is really facing. And let me tell you, guys, students, I was just talking a few days before, like there was a book, Silent Spring. It was published in 1962 by Rachel Carson, a lady. And that was regarding the excessive use of pesticides and DDT kind of things, So I'm talking about 65, somewhere 62, 65, So that lady wrote a book on it, and she suggested, that the book was, against the use of DDT. So there are, so many people against her. Particularly, the manufacturer of DDT and the whole lobby, and they were very against it, and they say, that DDT hardly harms. But later on, that we all know that DDT is a carcinogen, and it creates a cancer. So in that particular book, Rachel Carson, the lady who has written a book, she said, like the human arrogance, should be kept in control, and the nature should be allowed to take its own care and position. So that is what in the present situation, the COVID, like we never know, but still, something has happened, and we all are suffering because of that. So and because things will definitely be over in the months to come. So this is the time when we have to be really try to make the best version of our own self. This is the time we are really confined in the homes and with our family and all that. No, so this is the time to just improvise ourselves. We have to go. Some inner journey should be taken. We should take an inner journey and try to make a better version of ourselves. If you want to do something in a particular field, it's a time to utilize it. So I wish you all the best, and I hope this corona kind of things will really be will get over soon. Okay, thank you.
Thank you, sir. One of the participants, Nisa Garg ma'am, she actually wanted to ask question for you. I request Nisa Garg ma'am, please unmute yourself and ask the question directly. Nisha
Hello.
Garg, ma'am. Yes,
Hello.
yes, ma'am. You can ask.
Sir, I am Manleshwar Nisha Garg. As you know me, and you have suggested to patent my research work, and then
Okay.
I did it from patent of Mumbai
Yes,
office.
madam. Yeah,
Yes,
congratulations.
by the help of MPCST Bhopal, Dr. N.K. Chobe, sir.
Okay.
And now he told me that please trial it to the local people, and I
Okay.
also tried it on the local people. And unfortunately, there is a COVID positive people are also there. Then I tried on it. Then I got success on this. And I want to try. मतलब मैं इसे आगे आयुष विभाग में पहुंचाना चाहती हूँ, तो
Okay.
कैसे
Okay.
प्रोसेस होगी कि मैं इसको वहां तक पहुंचा पाऊँ?
Okay. I mean, you can just contact them, through their emails and all. And first, you have to contact them, and you have to say your sample and everything. Once you get any nod from them, I mean, any kind of
Yes, sir. Yes, sir.
communication.
I have collected the Google form, feedback form from them.
Okay.
Those who give as not as a commercial, but only for research and development work.
Yes.
And
Yes.
they
Yes.
fill
Definitely.
the feedback form. And may I proceed this feedback form towards the Ayush department or not?
No, you should, but at the same time, first you should get their yes for that. No, yeah. Let us wait for their consent to come, because
Yes.
you have to check the whole procedure, and definitely some individual you have to contact those who must be looking after it. And if suppose you wait for some few more days, no, so things will be normal, from new normal to normal. Then definitely I will suggest you, if
There is a
possible,
condition.
because
There is a condition not well, because in Manleshwar, corona is also entered from
yeah. Okay. Let
last
us
2
wait for a
weeks.
few. Let us wait for a few more days. I think everything will be normal. Then it can be done. Let us just
Okay.
maybe a matter of few weeks or few months. I hope everything will be normal, and then it can be
Yes.
done. So let us wait
Yes.
for it, and just be in touch with the Ayush department meanwhile.
And thanks to sir,
Okay.
as you
Yes.
suggested, and I did it. Thank you. Thank you so much, sir.
Thank you, ma'am.
So much.
Thank you. All the best. All the best. Thank you. Should I, Malabika? Should I take leave?
Yes, sir. I want to thank once again for your
Thank you.
very enlightening and beautiful, wonderful speech. And now we will proceed. We are proceeding to the end, towards the end of this webinar. So I will request the Professor Sahidul Islam, sir, Head of the Department of Chemistry, BN College, to offer vote of thanks.
Hello, Dr. Malavika. Am I
Yes, sir.
audible?
Yes, sir. Yes.
Yes. So good morning, everybody. We are at the last stage of today's international webinar on insight into the research in chemistry. That is the vote of thanks. First of all, I offer my heartfelt thanks to our Honorable Principal, Dr. Dhruva Chakraborty, for giving us the opportunity to conduct the webinar, in spite of the busy schedule of the institutions. My special thanks to the Honorable Research Persons, Dr. Suresh Bora, Synthetic Organic Chemist, Toronto Research Chemicals, Toronto, Canada, and Dr. Bijesh Pare, Professor and Head PG Department of Chemistry, Madhav Science PG College, Ujjain, Madhya Pradesh, also the President of ACT India, Association for Chemistry Teachers, for giving their kind consent to act as research person in this international webinar, in spite of their busy schedules. I offer my thanks to Dr. Malavika Bora of our department to act as coordinator and conducting the seminar in a nice way. I also thank to all the student participants and faculty participants for attending the webinar peacefully and patiently. Last but not the least, I thank all my departmental colleagues for their active cooperation and untied effort to make this webinar a grand success. Thanking you once again. I conclude. Hand over to
Thank you, sir.
Malavika.
Principal, sir, you want to say something?
I would like to again thank our resource persons, Dr. Bora and Dr. Pare, for their participation and active participation. To all participants from different institutes and different part of the planet to participate in this particular webinar, to the Department of Chemistry, all faculty members, and all the teachers, all the students of VN College and from other college. So thank you all.
Malavika, you are muted. You are muted.
Okay. Now it's audible, actually.
Yeah.
Yes, thank you all. Now, an announcement for the participants. You can provide your valuable feedback at the college website www.bncollege.co.in, which the link of which will be activated at 8 p.m. today, and it will remain active for 24 hours. So please provide your valuable feedback and download your e-certificate from the college website. Thank you all once again. Thank you, sir.